All right, so we are starting Chapter 6 today, looking at Section 6.1, which is a review of power series. Our goal in Chapter 6 is to find solutions of differential equations that come in the form of a power series. Now, power series are a major topic of discussion in a Calculus 2 class. You spend the entire end of that class looking at infinite series and power series, and so this is all review, but it's very important review for what we're going to be doing from 6.2 and 6.3. So very quickly, let's review what a power series is. We define a power series in x minus a, where a is some constant to be this. It's an infinite series that has this form. It basically looks like a polynomial of infinite degree, a constant plus some coefficient times x minus a plus another coefficient times x minus a squared plus another coefficient times x minus a cubed, and on infinitely. Okay, now we'll mention this again, but power series define functions because this x here is understood to be a variable. So I can plug in different values for the x in this series, and it produces different infinite series based on what I plug in for x. So that's important to remember. Now this series, we said it's a power series in x minus a. We'll also use this terminology. We'll call this a power series centered at a, that constant right there. Now, associated with infinite series and power series in particular, we have a number of different terms that are going to be important, and this is going to be a very quick review of those terms. You spend a whole ton of time in Calculus 2 talking about these, and we're not going to go through all of that detail here. So we're kind of trusting that you remember what a lot of this is. But for any given series, whether it's a power series or something else, we have a concept called convergence. And the idea here is to determine if this infinite series actually does add up to something, specifically some finite value, or if it doesn't add up to something finite, whether it shoots off to infinity, negative infinity, or just doesn't converge to a finite value for some other reason, like 1 minus 1 plus 1 minus 1 plus 1. That's a series that does not converge, but it also doesn't add up to infinity or negative infinity. So to be a little bit more specific in our language, in Calculus 2, we talk about how series, the sum of a series is interpreted to be the limit of a sequence of partial sums of that series. We're not going to be using that concept directly in this chapter, but that's to give a little bit more detail behind what we're talking about with convergence. If that sequence of partial sums has a finite limit, then we say that that's the sum of that series, and we would say that the series converges. If a series does not converge, then we say that it's divergent. Okay? Now, once again, like we said, this power series determines a function. So again, different values that I can plug in for x will determine different infinite series that this is turning out to be on this right-hand side. And it may be the case that for some values of x, this series converges, but for other values of x, it diverges. And so when we talk about the interval of convergence, we're talking about the set of all x values for which this series converges. And the reason we use the term interval is because it always comes in the form of an interval. And we can even be a little bit more specific about what that interval looks like. So for example, if you take a look at this infinite series, you should be able to determine that this series will definitely converge when x is equal to this value a. And the reason for that is because all of these terms after c naught, I can see are going to equal 0. A minus a is 0, and so I get a 0 here, and so on and so forth. So that infinite series actually collapses down to something that's not an infinite series, it's just this constant c naught. So it's always guaranteed that a power series will converge for at least the value a. But then if it converges for more values than just that, the interval, or the set of all x values for which it does converge, will look like one of two things. It will look either like an interval where that number a is exactly at the center of that interval, or it'll look like the set of all real numbers. So that really gives us three possible cases. Any power series will converge for either just the value a, or an interval centered at a finite interval centered at a, or the set of all real numbers. Okay? Now, the interval, because if the interval has finite length, so it's kind of like the second case that I just said there, then it might look something like this. Okay, and here we're using the terms absolute convergence and divergence. We'll talk about those terms in a minute, but let's just think of this as just convergence for a second. If we determine that a power series converges on some interval of finite length centered at this value a, then a being at the center means we can go the same distance to the right as we would to the left to get to the endpoints of that interval. And whatever that length is from a to either endpoint, we call that capital R, and we refer to that as the radius of convergence. So the distance from the center of that interval to either endpoint, we call that the radius of convergence, typically call that capital R. That interval can be notated this way. The absolute value of x minus a is less than r. That describes this exact same interval right here. Okay, if the power series in question converges only for the value a, then this interval collapses down to just that point a. And in that case, we would say that the radius of convergence is 0. There is no distance from a to either endpoint. If this interval is not finite in length, but in fact infinite in length, meaning the interval of convergence is the set of all real numbers, then we'd say that the radius of convergence is infinity to describe that scenario. Okay. Absolute convergence, we have a concept of absolute convergence which applies to more than just power series, but what absolute convergence means is that if we take our series and we take the absolute value of all of its terms and then add up all of those so that all of the terms are non-negative, if that converges, then we say that the original series converges absolutely. Now, in some cases, that's automatic, because in some cases, none of these terms ever come out negative, so taking their absolute values doesn't necessarily change anything. But in many other cases, for example, if Cn is alternating between positive and negative numbers, we may end up with terms in this power series that are negative, and so taking their absolute values actually does create a new series. But that's what absolute convergence is. Okay? And one thing that we know about power series is that for a power series, if we look at its interval of convergence, a power series is always guaranteed to converge absolutely within its interval of convergence. And it may not occur, that may not happen at the endpoints of that interval, but it will always happen for any value of x that's in the interior of that interval. Okay? So that's an important thing that happens with power series. We're guaranteed absolute convergence for any value of x that's within the interval of convergence, but not necessarily at an endpoint. Okay? And then in Calculus 2, you also talk about a whole bunch of convergence tests, ways of determining whether or not a series of any kind converges. And when looking at power series, one that is especially useful, that you use a lot in Calculus 2, is the ratio test. You may also remember the root test, but for us, the ratio test is going to be sufficient for what we need in this chapter. So the way the ratio test works is it's a way of determining whether a power series will converge or diverge for specific values of x. And what it looks like is if you look at the nth term in this sum, so just some general term that we call the nth term, and then you look at the term that comes right after that, so the n plus 1th term, and create a ratio out of those. Put the n plus 1th term, which would look like this, over the nth term, which looks like this. Take the absolute value of that ratio, and then take the limit of that as n goes to infinity. Okay? The ratio test says that if that limit is less than 1, then the original series will be guaranteed to converge absolutely. Okay? But if that limit is greater than 1, then this limit will be the original series is guaranteed to diverge. If that limit is exactly equal to 1, then the test is inconclusive, and we have to figure out a different way of determining convergence or divergence there. Okay? So the purpose of the ratio test for us is that it helps us determine what our interval of convergence looks like. So here's an example where we're going to do that. We want to find the radius and the interval of convergence for this power series. Okay, so first of all, the power series is not exactly in the form that we want it to be. We do have a coefficient in front of something that looks kind of like that factor that we saw in our definition of a power series, but that coefficient of 4 is problematic. If you notice right here, it should be of the form x minus a, not a constant times x minus a. So that's not that bad, because what we can do is factor a 4 out of here. Now remember, if we factor a 4 out of these parentheses, that 4 is being raised to the nth power. And so we have to keep that in mind. Okay, so this is equal to n to the power, or n equals 0 to infinity, the sum from n equals 0 to infinity of 3 to the negative n times 4 to the positive n times x minus 5/4 to the n. Okay, let's write that a little bit differently. I can combine these two things. This is the same thing as the sum from n equals 0 to infinity of 4/3 to the power of n times x minus 5 to the 4th, or sorry, 5/4 to the power of n. Okay, so I've taken my series and I've put it in a slightly different form, and our goal now is to determine the radius and interval of convergence. Our ratio test is our go-to test for that. So what the ratio test says is I want the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term. So what would that look like in this case? The limit as n approaches infinity of the absolute value of the n plus 1th term is just going to put n plus 1 in each of these exponents here. So that becomes 4/3 to the n plus 1th power times x minus 5/4 to the n plus 1th power. And down here, we want the nth term, so those n plus 1s are going to become n's, 4/3 to the n, x minus 5/4 to the n. And this simplifies in a really convenient way. So this is equal to the limit as n goes to infinity of 4/3 times x minus 5/4. So you should be able to see how that simplifies with no trouble. Now you'll notice that there's no more n's left in here. So the limit is, I can basically make that go away. This, for any value of x, is essentially just a constant in here, and the limit as n approaches anything of a constant is just that constant. So I'm going to lose the limit here. And in addition to that, 4/3 is already a positive number, and using the multiplicative property of absolute values, that 4/3 can just come completely out. Okay, so 4/3 times the absolute value of x minus 5/4. Now, what is it that we actually want from this? Well, remember, we want to determine for the interval of convergence, and that's going to mean that we want to determine all values of x for which this power series, the original power series, converges. According to the ratio test, we're only guaranteed that that's going to happen if this is less than 1. Okay? But if that's less than 1, notice this is the same thing as saying I can create a compound inequality out of this. It's the same thing as saying this. Right? Same thing. Now, if I solve that, so basically I would be multiplying all three of these by 3/4 to get rid of the 4/3 there, and then adding a 5/4 to both sides, you will end up with this. Okay? And that determines my interval of convergence. I'll rewrite it in a different form in a little bit. Okay? But that would be my interval of convergence. Now, it is possible that my interval of convergence will include these endpoints as well. So, for example, I don't remember if I plug a 1/2 into this, or into this inequality right here, this guy will come out exactly equal to 1, not less than 1. And the ratio test is inconclusive for that case. So what we do is we go back to our original power series, and I can do it in this form right here, and I plug in these endpoints, 1/2 and 2. I plug both of those in for x, and then look at the resulting series and make a determination using maybe some other test whether that converges or not. Okay? So for example, if I plug in a 1/2, let's use this space up here for that. n equals 0 to infinity of 4/3 to the n times 1/2 minus 5/4 to the n. What is that equal to? Well, this is the series from n equals 0 to infinity. This is 4/3 to the n. 1/2 is the same thing as 2 fourths minus 5/4 is negative 3/4 to the n. And this is equal to, I really did not leave myself enough room here, n equals 0 to infinity. I can combine these. 4/3 times negative 3/4 is negative 1. That's negative 1 to the n. And this diverges. I know this because what does that series look like? Negative 1, or if I plug in a 0, that's positive 1. And then my next term is negative 1. And then my next term is positive 1. So it's 1 minus 1, plus 1 minus 1, plus 1 minus 1. In Calculus 2, you look at that exact series and you show it diverges. What would happen if I put a 2 here instead? Well, if I put a 2 here instead, the only difference between this series that series and this one is that this becomes a positive 3/4, which means that sum becomes the sum from n equals 0 to infinity of 1 to the power of n. But 1 to any power is just 1, so it's really an infinite sum where every term is equal to 1. 1 plus 1 plus 1 plus 1, and that diverges to infinity. So basically what that discussion says is that our interval of convergence will not include these two endpoints. It's going to diverge for those. Okay. Now with that, how do we determine the radius of convergence? Well, look at our power series. Once we simplified it down, it looked like this. That 5/4 right there, that's A. So that's at the center of this interval. And remember, our radius of convergence is just the distance from that center to either endpoint. So for example, if I did 2 minus 5/4, that would give me that radius. So R is going to equal 2 minus 5/4, which equals 3/4. There's my radius of convergence, and my interval of convergence is going to look like this, 1/2 to 2. Okay? I didn't make very good use of my space here, and I also didn't write out what it looked like when I checked this endpoint in my original series for convergence, but this is meant to just be a review, so we're going to be a little bit lax on how much we show here. Okay, so like we said on the previous page, any given power series determines a function. So I can say that this general power series here is equal to f of x, and then just refer to that as f of x. Now the domain of that function is exactly the interval of convergence for this power series, because any values of x that are outside of our interval of convergence are values for which this series diverges and is thus not equal to anything. It would make sense for those to not belong to our domain. So the domain of our function is the same thing as the interval of convergence. Now you talk about some important theorems in calculus, which we're going to mention here. We're not proving any of this here, but we're going to be using them. So this is extremely important with power series. If you're looking at a power series on a particular interval of convergence, you can show that that function is both continuous and differentiable on that interval of convergence. And not only that, you can both differentiate and integrate that series term by term. That's extremely, extremely important for what we're doing in this section. So not only is it differentiable, but you differentiate it as you would a polynomial. You use the same power rule on each term of this power series to differentiate that function x. Similar with integration. Okay. Another really important property of these power series, which you may or may not have seen in Calculus 2, but it's this property that's going to make our method possible in section 6.2 and 6.3. When we're solving DEs using these power series, this property is what makes the whole thing possible, and it's called the identity property. What the identity property says is that if you have a power series, here's your general power series, and it's identically equal to 0, meaning it's equal to the function 0, Not just equal to 0 for certain values of x, but equal to 0 for all values of x. That's what that means, okay? And if our power series has a positive radius of convergence, and what that means is that the interval of convergence is more than just a. It has an actual interval with a positive radius. Then the identity property says that that only happens when every single one of these coefficients equals 0. That means every single term will equal 0, and of course, an infinite series where every term is equal to 0 sums to 0. But the identity property is saying that there's no other way for a series to be identically equal to 0 with a positive radius of convergence unless all of these coefficients equal 0. Okay, so we'll show where we're using that property once we get to an example of solving a DE. Okay, so don't forget that. Another term that you may not have been introduced to in calculus 2, it kind of depends, you might have seen it, is the term analytic. So we say that a function f is analytic at a point A if it can be represented by a power series centered at that point A with a non-zero radius of convergence. Non-zero meaning it would be either positive or infinity, right? Furthermore, if that function f happens to also be infinitely differentiable, then it's guaranteed to be analytic at every point in its domain, and that power series is what we call a Taylor series, centered at A. Okay, so this is what you talk about at the end of a Calculus 2 course, Taylor series. Remember, a Taylor series is just a power series. That's all that it is. But when we use the term Taylor series, we're talking about a specific formula that helps you come up with the coefficients on that Taylor series. And in particular, it's not just any power series, it's a power series that's equal to a specific function, f, and f is used in the determination of those coefficients using this formula. So you derive this in Calculus 2, we're not going to do that here. Of particular importance is the Taylor series centered at 0. When this a here is equal to 0, then that special case we refer to as a Maclaurin series, and that would look like this. It's a little bit simpler looking. In Calculus 2, you go through the process of finding Maclaurin series for several common functions. So I can pretty much guarantee that the first Maclaurin series you would have derived is the exponential function e to the x. That's an extremely important one. But you would have also looked at cosine, sine, inverse tangent. You might have done the hyperbolic cosine and hyperbolic sine. Natural log of 1 plus x is a common one. There's a reason why we can't do natural log of x, because that's undefined at 0, and so it wouldn't have a Maclaurin series there. And then actually before you even talk about Taylor series and Maclaurin series, you derive this one. 1 over 1 minus x equals this Maclaurin series right here. So these functions all have these, standard power series, these Maclaurin series that you should have seen, and you've probably at least used these top 3 so much, hopefully, that you would have them memorized. They're so incredibly common. In fact, we have even mentioned these 3 back in chapter 4 when we talked about Euler's formula. I think it was section 4.3 where we introduced that. So anyways, as these are all power series, every single one of them has a specific interval of convergence, and those are given here, okay? We will not be deriving any of these because you spend enough time in Calculus 2 doing that. This is just a reminder of what some of those common Maclaurin series look like, okay? Now I'm going to do this next example on the next video, but just to introduce what we're doing here, when we use these power series in solving differential equations, it's important to know how to do arithmetic with them. So you can add, subtract, multiply, and divide power series. And you can do it term by term as long as you're restricting yourself to the interval of convergence for that particular series. You can also come up with new series from old ones by using function composition, which we're going to have to do in this example right here. So I'm going to save this for the next video, but what we're going to be doing there is using power series arithmetic to come up with a new power series for a given function.